So this device that we've been talking about that has been converting heat into work is called a heat engine. So the formal definition of a heat engine is a device that operates in a cycle and produces net positive work while receiving heat from a hot reservoir and rejecting heat to a cold reservoir. So let's just review a few parts of this definition. First of all, this machine has to operate in a cycle. And remember, that's because we need to continuously convert heat into work. It produces net positive work. That means that the work that it does on its surroundings needs to be bigger than the work that the surroundings do on it, so that the net work, the work over the entire cycle, is positive. And then this definition also shows that there has to be two reservoirs. So it's receiving heat from a hot reservoir and rejecting heat to a cold reservoir. Now the next thing we want to talk about is the thermal efficiency of a heat engine. So when we use the term thermal efficiency, that's specifically talking about how good a job a heat engine is doing at converting heat into work. So the definition of efficiency is the desired output divided by the required input. So another way to think of this, the desired output is the thing that we want this machine to do for us. So in the case of a heat engine, we want it to produce work. The required input is the thing we need to supply to the engine in order for it to do its job. So that's the heat transfer from the high temperature reservoir. So we rewrite this definition in terms of those variables. So the numerator here is the net work of the cycle. So that's the net work, not just the positive work, but the net work, because we need to account for the fact that we need to use some of the work produced in order to run the cycle. So the numerator is the net work. The denominator is the thing we need to supply to this system in order for it to do its job. So that's the heat transfer from the high temperature reservoir. And notice those would have the same units, so the efficiency does not have units. Another thing that's useful to remember when we're looking at thermal efficiency is that the net work of any cycle is equal to the net heat transfer. So we could replace the work of the cycle by QH plus QC, and those are always going to be the same for any cycle. So if we want, we can write thermal efficiency purely in terms of the two heat transfers with the reservoirs. Now remember that these Q's have signs. QH is always positive and QC is negative. So the numerator is going to be smaller than the denominator and the efficiency will be less than 1. So we're making use of this fact, this characteristic of any cycle, when we write the thermal efficiency like this. Now the cycle that we already looked at, or the heat engine that we already looked at when we were looking at converting heat into work, it has a name. We didn't give it a name at the time, but it's called a Carnot cycle. So the cycle that we just described was a Carnot cycle. And a Carnot cycle consists of 4 processes: constant temperature heat addition, adiabatic expansion, constant temperature heat rejection, and an adiabatic compression. So those are the 4 processes that we looked at. Now in addition to that description of those 4 processes, for a Carnot cycle, all of those processes must be reversible. So remember, a reversible process is one with no friction, no sudden expansions, perfectly quasi-equilibrium processes, no sources of irreversibilities at all. So if the cycle has no irreversibilities, then it's impossible for us to build another cycle that has a higher efficiency, because you cannot produce a cycle that has a higher efficiency than a reversible cycle. So a Carnot cycle is very important because it's going to place an upper limit on the efficiency of any heat engine. So we want to investigate the efficiency of a Carnot cycle, and we're going to be doing that over the next little while. So the Carnot efficiency is the thermal efficiency of a Carnot cycle. We have a general definition of thermal efficiency, but it turns out we can show that for a Carnot cycle, that efficiency is equal to 1 minus Tc over Th. So notice, instead of being written here in terms of work and heat transfers with the surroundings, for a Carnot cycle, we can determine its efficiency purely based on the temperature of the two reservoirs that it's operating between, Tc and Th. We're going to go through and develop that equation in a little while, but for now we're just stating it as a fact. So the role that this expression plays is it is the maximum possible efficiency for any heat engine operating between reservoirs at Th and Tc. So this is known as the Carnot efficiency. So let's do an example here. Let's say we have a thermal power plant that is operating with a steam supply, and that steam could be produced by any source of heat. And the steam is at 500 degrees C, and we're cooling that thermal power plant with a river that is at 5 degrees C. So these are the temperature limits that that heat engine is operating between, 500 degrees C and 5 degrees C. So we can use just those two temperatures to figure out what the Carnot efficiency is. So that's what we'll do here. So we have our expression for the Carnot efficiency. Important to realize that the temperatures that we put in here have to be in an absolute scale. So because we're working in SI here, we need to convert those two temperatures to degrees Kelvin. So Tc is 5 degrees, that's our cold reservoir, so 5 plus 273. And Th, our high temperature reservoir, is 500 degrees C. So remembering to add 273 to get to degrees Kelvin. And this gives us an efficiency of 64%. So notice that's the maximum possible efficiency for any heat engine operating between those two temperature limits. So there's a very significant amount of heat that is rejected to the cold temperature reservoir. And notice for a thermal power plant like the Queen Elizabeth Power Station just upstream of Saskatoon, that QC in this discussion is the heat being rejected into the river. And this is why the river doesn't freeze in the winter in Saskatoon, is that a very substantial portion of the energy being put into the cycle actually ends up rejected and warms up the river. Now what we want to do is show where that expression comes from. So 1 minus Tc over Th, where does that come from? Well, we're going to do that by going back to the Carnot cycle, those four processes that we discussed earlier, and look at them to determine what the efficiency of that cycle is. Two of the processes in that Carnot cycle were adiabatic processes, and we're going to use an ideal gas as our working fluid. So if we have an ideal gas with constant specific heats undergoing an adiabatic process, and like I say, that's two of the four processes that are going on in a Carnot cycle, we can show that PV to the K is a constant. We're going to be doing this quite a bit later in the course, but this process, no heat transfer, ideal gas, constant specific heat, is a polytropic process. And it's not just any polytropic process, it's a polytropic process where the polytropic index is equal to Cp over Cv, the ratio of specific heats. So two of the four paths on the PV diagram for a Carnot cycle are polytropic processes with the polytropic index equal to Cp over Cv. So this is information that we need in order to develop that expression for the thermal efficiency. So PV to the K equals a constant describes a reversible adiabatic process for an ideal gas with constant specific heats. Now, here's what our Carnot cycle looks like on a PV diagram, and we've seen this before. So these two processes, from 2 to 3 and from 4 to 1, follow PV to the K equals a constant. So we have a description of those two paths. So now we can turn our attention to showing that this equation is true. We begin that process by going back to our definition of thermal efficiency. The work for the cycle divided by the heat supplied from the high temperature reservoir. Now the only difference here is I've written the numerator and the denominator on a per unit mass basis. So we have a lowercase w and a lowercase q, but the ratio of course is still the same. First thing we do here is we represent the work for the cycle by QH plus QC. We've talked about that before. The net work for the cycle is equal to the net heat transfer. And then we just rewrite this as 1 plus QC over QH. So this is what we have so far. Now notice this is already looking quite a bit like that. Same general form, but of course this is temperatures, not heat transfers, and there's a change in this sign here. So we have a little bit of work to do before we get to this, but we're well on our way. Now we want to start to look at these processes. Notice what we need to investigate is QC and QH. We need to figure out how is QC and QH related to these two temperatures. So we begin to look at each of these processes to figure that out. Well, the process from 1 to 2, remember, is a constant temperature process. So its delta U is equal to 0. Therefore, the heat transfer is equal to the work transfer. Remember, Q minus W is delta U. If delta U is 0, Q equals W. So 1 to 2, Q equals W. So we can figure out what Q is by looking at W. And that's what we're doing in this line. So we're after QH. First of all, we know that the heat transfer with the high temperature reservoir all happens during the process from 1 to 2. So that's what the first part of this is doing. QH is equal to Q from 1 to 2. So that's our QH. The next thing we realize is that that Q is equal to the work transfer because delta U is 0. Now, this is an ideal gas undergoing a constant temperature process, so the work transfer is equal to R, the specific gas constant, times the temperature this is happening at. So remember, the temperature during this process is TH. So RTH times the log of V2 over V1, and we can rewrite this volume ratio in terms of a pressure ratio, because remember, P1V1 equals P2V2. So V2 over V1 is P1 over P2. So that is the heat transfer being supplied to this cycle. RTH log P1 over P2. Now we can do exactly the same thing as we've just done here for this process from 3 to 4, because it is also a constant temperature process. So when we do that, delta U again is 0. The heat transfer to the cold reservoir is Q3 to 4. Remember, heat is being transferred from the hot reservoir here. No heat transfer there. No heat transfer there. And heat's being transferred to the cold reservoir here. So QC is equal to Q34. And again, because it's constant temperature, there's no change in internal energy, so Q is equal to W. And because it's constant temperature, the work is RT times the log of the volume ratio, which again can be converted into a pressure ratio. So QC is equal to that. So we bring these two expressions for QC and QH back into our efficiency expression, and we get efficiency equals 1 minus RTC log P3 over P4, RTH log P1 over P2. I want to just address where this negative sign came from. Notice up here, QC is written as RTC log P3 over P4. Here it's written as RTC log P4 over P3. So I've inverted this, and that produces this negative sign out front. So that's where that negative came from, is just by flipping these pressure ratios over. Now, We seem to be getting sort of close to our final goal, which is 1 minus Tc over Th. We can see that these r's are going to cancel. That's no problem. And we can see that we have Tc over Th in here, but we still have these pressure ratios, and we've got to show that those two things also cancel out because it's not immediately obvious. So what we've looked at so far in this development is the details of that process and this process, because that's where QH and QC are happening, to show that what remains here is also just equal to 1. We have to look at this process and this process, because these two are what link the pressures up here to the pressures down there. So that's what we're going to do. So we'll begin by looking at process 2 to 3. Well, remember, this is PV to the K is a constant. So P2 over P3 equals V3 over V2 to the K. So that's just PV to the K is a constant. And this is another instance where we want to take an equation that relates pressures and volumes and change it to an equation that relates pressures and temperatures. So we want to get rid of these V's and get temperatures in there instead. So we do that by substituting the ideal gas law into there. So each of these V's is going to be replaced by RT over P. When we do that, the R's cancel, and so this volume ratio becomes P2 over P3 times T3 over T2 all to the K. We take this pressure ratio and move it over to here, and we get P2 over P3 to the 1 minus K equals T3 over T2 to the K. And then we get rid of this exponent by raising both sides of this equation to the power 1 over 1 minus K. So we just have our pressure ratio here. This temperature ratio then has an exponent of K over 1 minus K. And here we recognize that T3 is Tc and T2 is Th. So we just rename those temperatures Tc and Th. So by looking at this process, we've got this pressure ratio written as a function of the temperature at those 2 points. So realize we can do exactly the same thing for the process from 4 to 1. And if we do that, we get the pressure ratio from 4 to 1 being Th over Tc to the same exponent as this. So if we compare these two expressions, notice that the only difference on the right-hand side is these are the inverse of each other. So we can invert either one of these, whichever we want, and that makes them equal. And so that means that P2 over P3 is equal to P1 over P4. So P2 over P3 is equal to P1 over P4, or P4 over P3, just bringing that one over here, is equal to P1 over P2. So bring P3 up there and P1 down here. So those pressure ratios are equal. And if you recall, those are the two pressure ratios that we have in our current expression for the thermal efficiency. So indeed, these logs of pressure ratios are equal, and therefore they cancel out. And of course the R also cancels out. So that brings us to the conclusion that the thermal efficiency of a Carnot cycle is 1 minus Tc over Th. Again, a very useful expression because it places an upper limit on the efficiency of any heat engine operating between two temperature limits.